Hello everyone, and most welcome to today's webinar, Unlocking the Potential for Sweden's Power, Mobility and Industry. My name is Åsa Agervald, and I'm the Business Unit Manager for AFRY's Business Unit Thermal and Renewables in Sweden. I am one out of 5 presenters today, and before we start I will give the other ones also a time to introduce themselves. So I hand over to Pedro.
Hi everyone, my name is Pedro Raposo. I'm working at AFRY as a Director Power to X, and together with me I will also have Simon.
Yeah, so Simon Sjöstedt, working at the AFRY Management Consulting, and I will be part of the presenter of the mid section here. Peter?
Yes, Peter Kjellander, Project Manager at AFRY. I'm working with more the technical aspects of renewable energy and also increasingly with the feasibility and implementation of green hydrogen solutions.
And finally, Marcus.
Yeah, so Marcus here, part of the management consulting team based out in Oslo. I tend to deal a lot with power market modeling, and we do a lot of power market and electricity price projections based out here. So I will be talking a little bit about the power market implications part of this presentation.
Thank you. Okay, before we start, please ask questions throughout the webinar using the question panel, and we will cover as many as we can at the end of the webinar. And the slide pack and the recording will be emailed to you all attendees as soon as they are ready. Today we have an hour, and this hour will be divided into 5 parts. So I will start by giving it a background, why hydrogen and why now, and then we will continue with the demand potential in Sweden, followed by hydrogen supplies and the transportation issue, and followed by that power market implications, and finally some key messages before questions. So why is hydrogen such a hot topic right now? Well, the main reason why we are talking so much about hydrogen is its role in the decarbonization and the value that it can have in helping us achieve net zero. Hydrogen can actually be the only option to decarbonize certain sectors. Today we will focus on these 4 sectors that you see on this slide. Hydrogen is currently being used as feedstock in refineries, in ammonia and methanol production. And we have to recognize that the existing hydrogen production results in carbon emissions. It is produced from fossil fuels, mostly gas and coal. And this must be addressed by making hydrogen production low or zero carbon. Because as long as hydrogen is still required as a feedstock, then there are no alternatives really other than to decarbonize the hydrogen production. In industry, hydrogen can also be important, have an important role in new applications, such as being used as a reduction agent in the manufacture of steel. Here it appears that there are also few options to decarbonize steel production other than to use hydrogen. In other industrial uses, however, the role for hydrogen is not so clear-cut. For instance, if hydrogen is to replace gas in the production of process heat, it's possible that electrification could be a better option. In the second or the next sector, space heating in homes and other buildings, hydrogen boilers could replace natural gas boilers. But so too could other technologies, as for example installation of heat pumps. Here, it will depend on the age and insulation, but also on the practicalities in installing a heat pump. The UK, for example, is supportive of hydrogen and is currently carrying out numerous trials to test the use of hydrogen in the domestic situation. But we have to wait, however, because the government is not proposing to make a decision until 2026. In the third sector, the mobility sector, hydrogen can play a role in heavy truck and also in the public transport. And here, of course, there will be competition from electrification and the use of batteries. The case is probably clearer for the use of hydrogen, or rather its derivatives, ammonia and methanol, in the maritime sector, where long distances means that batteries are not feasible. And in aviation, work is underway to use hydrogen directly, or also to use low carbon hydrogen to make drop-in synthetic fuels. And finally, in the fourth sector, the power sector, hydrogen can play a role in a number of ways, from offering long-term energy storage to being combusted directly in combined cycle gas turbines. As it is dispatchable, then it can enable the deployment of additional renewables as well, and via fuel cells could offer off-grid solutions and offer ancillary services to the grid. Okay, and then we continue. The potential for hydrogen to play an important role in decarbonization in Europe has been recognized both on EU and national levels. What is notable, however, is that the billions of euros that will be required to deliver these strategies. On this slide, you can see the hydrogen strategy, the EU hydrogen strategy. And it sets out an ambitious deployment path for production of green hydrogen, requiring up to 450 billions in investments by 2030. It has targets for 6 gigawatts of electrolysis capacity, producing 1 million tons of hydrogen already 2025, and a target of 40 gigawatts, producing 10 million tons of hydrogen in 2030. And we have calculated that meeting these targets will require an additional of 11 gigawatts of offshore wind by 2025 in 4 years, and an additional 150 gigawatts by 2030. To put all these numbers in context, that's an additional of 900 offshore turbines by 2025. And by 2030, we would need additional offshore wind equivalent to the total installed renewable capacity in Germany today. It's massive. And if we lift the gaze further to 2050, the EU states that 25% of all renewable power could be used to power 500 gigawatts of electrolysis capacity. And again, we have calculated that this would require more than 700 gigawatts of offshore wind, equivalent to 70% of all EU generation capacity of all types today. Yeah, as you can see, it's a huge investments are needed, and they have to be fastly implemented. So most of these investments will, of course, be in their renewable capacity to provide sufficient green power, but we will also see investments in other parts of the value chain, such as the scale-up of electrolysis capacity, manufacturing capacity, and significant investments in hydrogen transport and storage, as well as investments by end users to replace existing equipment. So with this introduction, I leave the word over to Pedro.
Yeah, thanks, Åsa. And I will talk about the demand potential in Sweden. And Probably many of you know everything or most about hydrogen, but I will start a bit back to basic and asking you, what's hydrogen? And I think that we all know chemical formula H2, and it's the most abundant element in the universe, the lightest element known. But hydrogen is mostly associated with different words or concepts or assumptions. I think the first thought that it comes to my mind when thinking of hydrogen, and what I hear from people, is that it's explosive and dangerous. The opinion is actually starting to change and getting a bit more positive and looking at the future, environmental friendly. But then when you do a bit deeper analysis, you quickly understand it is expensive. And but most of the people know that it's a gas, or it's mostly used in gas form, and you can use it as a fuel. And unfortunately, many people, or a few at least, associate to a Zeppelin, and you have probably heard about the Hindenburg syndrome. And I normally say that it wouldn't be by the Hindenburg syndrome or the Hindenburg accident, we wouldn't be talking about hydrogen, because it would be already a reality. So I don't know if it's positive or negative, but it's a fact. And if we look at the hydrogen production in the world, on the next slide, we can see that we have production from renewable energy sources and from non-renewable. Of course, that if we look at different processes, the most interesting is electrolysis. Why is this? Electrolysis is actually an emission-free process, especially when you produce electricity from renewables, from sun, wind, or hydropower, and you use the electricity to split water, and then you have hydrogen and oxygen as a product, and that's how you have actually green hydrogen. But there are actually a few other processes, as you see in this table. And when we look at the global production in the world, the next slide, we have it a bit more distribution through fossil-free or non-renewable energy sources, like methane or methane coal, through syngas, or even coal, gasification of coal. Only about 3 to 5%, these figures are approximately, of course, and this is not Sweden, this is actually a world perspective. And only around 3 to 5 of the world production of hydrogen comes from electrolysis. And as we all know, not all electricity produced in the world is actually from renewable sources. So which means that the hydrogen process, or the hydrogen production, is actually not so environmental friendly as it is now. And if we go one step forward and we look at the most common process of producing hydrogen in the next slide, we can see actually, which is from natural gas, we can see actually that is a quite demanding, energy demanding process, requiring quite huge amounts of steam and heat, and it actually pollutes a lot. It's a very big polluter when it comes to CO2. This makes me wonder, but why are we talking about hydrogen when most of it is actually producing so much CO2 emissions? Well, because there is actually another option, which was the electrolysis that I mentioned, and it's not new. If we see it on the next slide, we have been producing green hydrogen since 1927. This is like two projects that one of them, at the left, was started in 1927, is in Rjukan in Norway, which was a plant for about 300 megawatts. As far as I know, we haven't built yet such a big, larger hydrogen plant. There are a few projects of something around 200 megawatts, and in that perspective, we have even a little bit larger connected to the green steel, but still not operating. This plant is not operating. It was operating until the end of the 70s. On Glomfjord in Norway, there was also quite large, 150 megawatts, that was operating from the 50s, early 50s to the late 90s, or sorry, early 90s. And both of them, they were used to fertilizer production through the HYBRIT process. And actually going to the fertilizer production comes to the next slide, where we can see that most of the production of hydrogen is actually used in ammonia for the fertilizer, which means that all the ammonia production in the world basically is produced with hydrogen that is not fossil free. It comes actually from natural gas producing quite a lot of amounts of CO2, as I mentioned. Well, if we apply this to Sweden, if we look at the next slide, where we have, this is a slide, in this picture we see just 2 days ago how the distribution between the electricity production in Sweden was. Something like 30% nuclear and around 65% depending, this is varying of course, on wind and hydro. So I think that this shows quite how Sweden is in a good perspective for a low carbon hydrogen production. I wouldn't say a green hydrogen production totally, because we do not have that totally, but we have very low carbon, which is quite kind for the environment. Well, why do we need hydrogen basically? The potential of hydrogen is huge, as we can see on the next picture. These are a few of the applications on the right side. Everything from green steel, like hydrogen as a reducing agent, ammonia, as we mentioned, methanol, jet fuel, fuel cells, so the transport sector, space rocket fuel even, possibly in the future gas turbines. Heat is also already a reality and in pilot scale, but already starting. Large scale energy storage, polysilicon wafer, solar cells, fat hydrogenation, you name it. It's quite a lot of potential. But this concept only makes sense if you produce it from the renewable energy through electrolysis and producing green hydrogen as oxygen as a byproduct. So we even have that possibility. Basically, this is what we show here is actually what we call power to X. The power to X concept means converting electrical power into something else, where you have at the core of the process electrolysis and hydrogen as the core of the power to X technologies. Some people say that power to X technologies will be able to provide almost a third of the global energy demand by 2050. So I think that power to X is actually a way or a key to decarbonization in the future. Looking at Sweden, what are the potential sectors for Sweden then? Well, you can see it on the next slide very shortly. Green ammonia, it is possible since we have such an interesting energy production in Sweden. So we have a good infrastructure we have a good possibility for creating a good infrastructure for producing green ammonia. Something that is not so much mentioned in Sweden, basically not even almost in Europe, which is like solar cells manufacture, where you need polysilicon. And well, hydrogen, large amounts of hydrogen are used to react with the 3-chlorosilane gas to produce silicon and polysilicon for the solar cell wafers. This has actually something that has been done in Norway a couple of years ago, but it has been moved, the production facilities have been moved to other countries, to some low-cost countries. But I see a potential that this could be done in a renewable way, where you can use actually renewable energy to produce hydrogen. Transport, hydrogen versus railroad electrification. There is also very interesting concepts in Sweden. You have the typical example of the Inlandsbanan, the inland of Sweden's railroad system, which is not electrified. And by using hydrogen, you could actually convert it to you can convert from fossil fuels for the usage of the train system. And you can even at the same time create a logistic system through the inland. So you actually do 2 in 1. You create a railroad instead of electrification. You create a fossil-free railroad instead of electrification, and you use the railroad for transporting hydrogen. I would also estimate that in Sweden we will need to store large-scale energy, and we cannot consider a future energy system without storing hydrogen, storing energy. I mean, because when we will go to more fluctuant energy production, we need to store the energy when we don't use it. But I think this is actually quite obvious to most of you. An interesting concept, quite emerging. There is a few reports and a few talks about this, which is what we call energy transfer, and comparing electrification versus pipeline. There are a few calculations that look at that when you're upgrading your grid versus creating a gas infrastructure, the costs are very interesting from the gas point of view. So in certain perspectives, in certain distance, it could be interesting and more interesting to use a pipeline instead of upgrading the grid, the electrical grid. But Sweden is actually doing already some things on this. So if we look not only the potential, we could look at the initiatives that are being taken already in Sweden. So I think that we are we have a very good perspective of developing this and putting in place all this potential in different areas. Unfortunately, it's taking time. I've been working with hydrogen since 2008, and 2008 I was driving actually a fuel cell car, and in that time I thought, aren't we doing this? Haven't we done this before? And it's been many years, and we still find it very difficult to implement an hydrogen society. But we will get there. I truly believe we'll get there. I would say that a very, very important issue is actually the competence. If you look at the next slide, I would say that there is already a competence demand. We at AFRY, we see that. We work in different projects with hydrogen, and we see that many people working in hydrogen are struggling to find competence. So here now I would say that we need competence, for example, on electrolysis, so electrochemistry. Handling of hydrogen is also something that is wanted, safety, and of course, everything related to hydrogen applications. And if we look at the long term, I would guess, and this is a guess that I say, long-term competence, if we see it on the next slide, I would guess that large-scale optimization and grid flexibility is something that we will need to look at. When we are already engineering large-scale plants from 200 to 800 megawatt hydrogen plants. And when we do this and we want to integrate both the hydrogen production and connected to the grid flexibility and the electricity production, this will require tools like AI or digitalization methods in order to optimize this process. I see also an emerging market for electrolysis when it comes to solid oxide state cells. They are much more efficient when it comes to traditional PEM and alkaline. And large-scale fuel cells is also very interesting. They will show up more and more, and the need will actually show up. And of course, new end user applications. What we don't know right now, I think that hydrogen, when we will establish a hydrogen society, and I say when, I don't say if, I believe that there will be even more applications that we can use from hydrogen. And looking at the competence, there is, just like to finish, I would like to mention this very good initiative in Luleå that in the north of Sweden, for those that are watching this that are not from Sweden, this university starting under a 10-year period is making a plan to create specific education on hydrogen and planning to educate and specialize 500 hydrogen engineers. I don't know if it sounds a lot or if it sounds too little, but I think that more and other universities, schools, research centers should actually take similar initiatives to educate, to train, to give and increase competence, because actually I would say that this is a challenge that we are seeing at the moment, and I think that we would need to put effort. Thank you, and I would like to give me my word to Simon.
Thank you, Pedro. So me and Peter Sjölander will present the hydrogen supply and the transportation issue. So if you can go to the next slide here. So the green hydrogen is in many ways very interesting, as it has potential to decarbonize several sectors and replace fossil fuel. But it also makes this sector quite complex, as there are many different parameters to take into account in order to actually find high potential ways to produce green hydrogen. And depending on the hydrogen application, both the future hydrogen demand, as Peter mentioned earlier, where it will be, for an example, is one parameter. The current and the development on the electricity grid, where the electricity will flow. If or where we will have the future gas infrastructure, and also renewable energy, how much and where the renewable energy will be in Sweden for this example. So these are several parameters which we will discuss during this webinar. So we can go to the next slide. So generally speaking, you could either produce green hydrogen at the demand side of the hydrogen demand side, or you can produce it where you have low carbon, very cheap electricity. And of course, you can also have a mix between these, where you have renewable energy sources and hydrogen supply at the demand place. But we will look at these two, which are these two examples of producing hydrogen, which are very different from each other and also illustrates our scenarios quite well. So looking at produced hydrogen at the site, you have some pros and cons with both of these, of course. And the positive here is that you don't need to investigate the distribution of electricity and hydrogen because you have it on site. And it also makes that the cost of transporting hydrogen, which could be quite big, is very, very limited. On the negative side, you're more dependent on the electricity area where you will have the price where the industry actually is, and it could be in the wrong place for cheap electricity. And also that you're connected to the grid all the time, so which is not always renewable energy, not even in Sweden. If you're looking at the other option, you could produce hydrogen where you have the cheap electricity. On the negative side there, you are more dependent on gas infrastructure to distribute the gas from the site to the demand location. And also that most of the production will probably be in north of Sweden, and most of the demand, at least now short term, but probably in the future as well, will be in the southern part or in the continent. So you need to export it quite far. On the positive side instead, you will see that we will have a low levelized cost of hydrogen, or the potential, which we'll show in the next slide. And also that it's possible to produce hydrogen for wind clusters, which Peter will discuss a bit later. So looking at this slide, in order to produce competitive green hydrogen, it's three elements which is extra important to have in mind. And the first one is the electricity price. The second one is the distribution of electricity and also distribution of hydrogen. And the third one is the production profile of the electrolyzer. And the production profile of electrolyzer will be discussed more in the market section in the end. So starting at the electricity price. In Sweden, we have, as you know, low carbon mix is about 1/10 of the European average. We also have very competitive prices, and especially price areas SE1 and SE2. So have that in your mind when you're looking at the graph to the right, where we have looked at the levelized cost of producing hydrogen in a Nordic context by 2025. And just to have that in mind as well, and this is just the cost of producing hydrogen, so it's not the distribution of hydrogen, which needs to be on top of this, of course. Looking to the left, the two left stacks, that's the more common way to produce hydrogen today, as Pedro mentioned, the steam methane reforming with and without carbon capture and storage. And then to the right instead, we have the way to produce green hydrogen, or hydrogen produced by electrolysis. And especially capturing prices for spot prices here in Sweden in SE1 and SE2. And if you look at the two right ones, so the electrolyzers where we have a big green field, you can see that the big green field here is the fuel of producing hydrogen. And in this case, the fuel is electricity. So as you can see, that's the majority of the cost of producing it. So with lower electricity prices, that will have a huge impact on the cost of producing competitive green hydrogen. We can also see in the Nordic context that more conventional way to produce hydrogen is still cheaper, but especially in SE1 and SE2, we can see that the cost is coming down quite a lot. and with lower average prices, hopefully more in the future, we will see that will be more and more compatible in a quite close future. But also to have in mind, as I said, the distribution is not part of this, and that could be a very interesting parameters to a very costly parameter if you're doing it wrong, so to say. And we can look at that on the next slide. So, as most of you are aware of, there have been a lot of discussion in Sweden regarding the bottlenecks regarding the Swedish grid, both transmission and a regional grid. And today Sweden has a very clear north to the south energy flow, where more or less most of the electricity is produced in the north, and the demand is mostly in the south. SVK is in their 10-year plan. They're investing a lot in new grid assets, but we have a fast changing energy environment where new production and new demand is coming quickly, so it's hard to be one step ahead. And especially in the future, when we will see that we have a large demand of hydrogen and also electricity from the industry in especially SE1. What's interesting then is what will happen with the electricity flow. Could it be, for an example, that the SE2 is pushing electricity both north to SE1 and also south, and that would change the energy flow of the electricity grid and also the constraints. Production of green hydrogen that's a risk that if it's produced on site, and if these sites are in places where you have grid constraints today, that could be even more constrained because you need more electricity to produce it. But on the other hand, you can also say that hydrogen could be a way, if it's producing it one way and then distributed to the demand side, it's actually another way to transport energy in a more cost-efficient way if you're looking at long distance of energy carrying. And I think that's an interesting topic to have in mind, that hydrogen pipelines in the future, and as Pedro said, it could actually be an interesting way to see a redundancy of energy transportation in Sweden, where you have the electricity grid more or less only today. Several studies has looked at this, and it could be it's a big discussion of where or if we should have a hydrogen and gas grid and where it should be. Today we just have the natural gas grid in the southwest, but the potential and both the production and the demand will be in the north. So it could be possible to maybe to have a gas pipeline crossing different electricity zones in Sweden. And this leads me back to my first slide, so we can look at that again. Because to understand if we should have a gas grid, for an example, of where the demand is, where you want to build your energy supply, you need to take all these type of parameters into account. And I've introduced a few here, and Peter will continue to discuss mainly the renewable energy supply parameter.
Yes, thank you, Simon. So starting out a bit here with the second aspect that Simon mentioned, where do we actually see that we will have a strong supply in renewable energy in Sweden? Well, first of all, the renewable energy has been sort of expanding rapidly, in particular in the last 5-6 years, and mainly through the onshore wind energy. And this level of expansion is sort of maintained also now. Currently in 2021, we have about 2.7 gigawatts installed, under construction, I should say. And in terms of produced energy, this means that sort of at the start of this year, we were at the level of producing around 26 terawatt hours of renewable energy from onshore wind power. And towards the end of this year, we will be at the level of approximately 35 terawatt hours. So it's moving fast. And this forecast that we see here is really reliable, as it is based on sort of binding contracts as provided by the turbine manufacturers, which are acting on the Swedish market. And as you see, the currently added production is very much focused to the SE2 area. But also if we look ahead a bit and in relative terms, we see that the expansion would also cover the other price areas in 2022 and 2023. And with all this added, up in 2024, we will be at the level of producing about 50 terawatt-hours per year. And the further outlook on this, looking a bit further ahead, well, the Swedish Energy Agency, they have an indication on that about 80 terawatt-hours should be produced from onshore wind power in 2040. But as you see, with this current rate of installation, this will be reached a lot sooner if we assume that this rate is maintained. And on top of this, we should not forget about the interesting development which we see also in the Swedish offshore wind energy, which may also give a substantial supply, and which in particular will also be in the southern half of Sweden. With this, we can move to the next slide. If we now also look back at this on the first aspect, which Simon mentioned, where we have more of a local production, which we can see more linked to one particular supplying wind farm, for instance. And this situation has been driven by that there are potentially very large wind farms in pipeline, and this is also related to the development of turbine technology, and with this taking the full advantage of given permits, for instance, means that there's a situation where we have what we can call possibility for an excess production in relation to the grid capacity. The grid capacity can increasingly often be seen as a bottleneck for many projects in terms of how much they would potentially be able to produce. However, this curtailed production from a single wind farm might not be optimal if you think about the for the hydrogen production from a a standalone solution with a wind farm and the hydrogen production, this is visualized in the first image, where we see the variability in production from the wind farm, and that can be challenging for the utilization of an electrolyzer. But in this equation, you also need to take other aspects into consideration, such as storage and transport solutions, of course, as well. But we see that there are interesting options also arising when we're analyzing overlaying production from more wind farms in regional clusters. They can provide an interesting synergy, and in particular if the grid connections is a constraint in these regions. So with this, we're back on focusing on the interesting development for hydrogen production is also closely linked to where we see the significant expansion of onshore wind farm development, and which we see will come in the coming years, I should say. With this, I hand over to Marcus, who will introduce us a bit more to the market implications.
All right, thanks, Peter. Okay, I will talk a little bit about power market implications, but in order to do that, I think that I will have to start to ask effectively a question how electrolysis plants should operate in the market, right? So depending on how the electrolysis technology and how effectively the plant is operated, the electricity price that it captures, and therefore the fuel cost to the electrolyzer, that can vary quite significantly. So effectively what you see here on the screen is a simple example of an electricity price duration curve, so which shows the price distribution of over the year. So on the far end of this price duration curve, prices are around zero, and this indicates that there are surplus energy and effectively some curtailment in the market. Now the operational characteristics of electrolyzers is a little bit of a kind of an equation you have to optimize. So if you have a base load need for hydrogen or a continuous need for hydrogen, you might need to run it further up the price duration curve, and that is going to lead to higher variable costs and a higher average cost for your hydrogen production or for your hydrogen. And then if you think about producing hydrogen from just the surplus generation, then your capacity factor of the electrolyzer plant needs to be lower, because there are only in a certain amount of hours that you have very low price hours and the surplus of this kind of renewable generation. And then you operate only during a small part of the price duration curve, which means that you have lower variable costs. But also, when you have low operational hours, you are likely to have to oversize your electrolyzer. You have to invest in storage. So therefore, this equation is a little bit different, and the levelized cost of hydrogen can go up because of that. Now, of course, there are other operational characteristics. So you can produce hydrogen off-grid connected to a dedicated wind farm. Now, this is not necessarily the cheapest option available for just producing green hydrogen. And it also might be obvious that the implication for the power market are none when the electrolyzers aren't really connected to the power grid. I think it's going to be reasonable to assume that the price elasticity on sort of the demand curve for hydrogen is not the same for all sectors. So this type of operation will be different depending on what sector we're talking about and who's effectively the owner of the electrolyzer. So for an example, if you use hydrogen for feedstock to produce like added value products such as green steel, which is very relevant for the things that we talk about and very relevant for Sweden, it's reasonable to assume that this is less sensitive than the use case to produce hydrogen for an example, light duty transport, where you have other low carbon options that are effectively cheaper, such as batteries. And now, how far up this kind of price duration curve you want to travel is obviously going to depend on the price sensitivity and the use case of the alternative, or sort of the cost of the low carbon alternative. Now, this tends to be blue hydrogen, so essentially steam methane reformation of natural gas coupled with carbon capture and storage, if it is to be low carbon effectively. Otherwise, there are cheaper options in gray hydrogen, of course. So next slide. So when talking about the deployment of renewables and electrolysis in tandem, I like to say growth begets growth. So a growth in these technologies in the long term can spur what we could call a virtuous cycle of build. So intermittent renewable growth tend to depress power prices. So let's say that you have a power market, you add a lot of renewables into it, it depresses power prices during its hours of production because of its variable production profile. So during this specific hour, it tends to lead to more hours of low prices. And this renewable asset is unable to capture the value of this of the sort of average annual electricity baseload price in any given power market. So, and this is what is known as the cannibalization effect. Now, theoretically, if you have an unconstrained renewable resource potential in a power market, so renewables should theoretically stop when it's no longer profitable to build, as this cannibalization effect becomes worse. And effectively, if costs doesn't go down. Now, what the flexible electrolysis is able to do is it's able to soak up these hours and follow the renewable production profile. So it can counteract this cannibalization effect of renewable renewables. But at the same time, that implicates that you have self-cannibalization for the electrolyzer as well. So as you have less cannibalization for your renewables, power prices rise, and you cannibalize the electrolyzer instead. But this is what you could say a virtuous cycle of build. So as that increases, then you can increase renewables, power prices go down, electrolysis are built, less cannibalization of renewables, and this could keep on going for quite a long time. So depending on a lot of different aspects. So for an example, resource potential, you can get a stop in renewable investments, which in theory then should stop also electrolysis build, and also many different aspects that is technical, and financing is also something that obviously cannot keep this cycle going forever. So on the next slide, and it's a little bit of an example for how merchant electrolysis would effectively be deployed over time. So merchant build of electrolysis is something that would become viable as the technology costs for both renewables and the technology costs for electrolysis fall extensively. So what you see on the picture here is that as fixed costs for your electrolysis plant, if that goes down, you could at some point reach what you call cost parity, and then you would be able to run your electrolyzer over a higher amount of time of the price duration curve, pretty much. So you can run your electrolyzer longer with a higher load factor, but still keep your costs at the same level if capex goes down. So once you reach this cost parity, then you can start to see this sort of reaction to the market, and you can start to see what we say is a merchant build. Now, prior to this, you will have to, before this kind of cost reduction can happen, you have to deploy capacity through either subsidies, or you might be able to drive deployment through, for example, PPAs and whatnot. So next slide. So I think it makes sense to, given that background, it's good to try to give sort of an indication of how the Swedish and the Nordic electricity market can be affected by some of these larger mentioned projects in the midterm, and especially when we talk about the green steel projects, right? So at AFRY, we do have quite extensive power market modeling capabilities, and one of our core offerings is that we do supply independent projections for long-term electricity prices for all European energy markets, and the Nordics included, of course. So just on a brief comment on this like power market situation in the short term is on the left-hand side, we have this relative price difference between the Nordic price zone, both what happened in 2018 and as a result from a market modeling exercise that we do. And then on the right-hand side, you see the evolution of the energy surplus in Sweden in the same modeling exercise. Now, this energy surplus is effectively mostly due to a deployment of onshore wind power. And as you saw previously on one of Peter's slides, this is mostly happening in the northern price zones, so in the northern price areas. Now, although we have this like growing energy surplus from wind, we are not curtailing it. So we have large amounts of reservoir hydropower in the region, which prevents this curtailment. and any surplus production can be saved and we can use it later, or it can be exported. Now, 2018 on the left-hand side here is shown as an example for that price area deviations in the Nordic market historically wasn't really apparent, not at this at an extensive level at least. But this has become quite a reality in 2020, 2021, very visible, that we have a north-south price split. This is partly driven by hydrology, partly by an increasing supply-demand imbalance between north and south. And of course, nuclear closures in the south, and we also have quite a lot of transmission constraints that have started to appear. Now, price difference like this tends to be exacerbated by high prices in neighboring continental markets. And this is very true right now, you could say, because this indirectly will have a say in the price evolution also of the Swedish Nordic price zones. More so for the northern price areas due to these transmission bottlenecks that we have. Now, price area deviations such as this is something that will likely continue to be apparent in the market until the transmission grid is expanded in order to offload this energy surplus that is being built up. But as Simon mentioned, the lead times of transmission grid is long, tend to be many years before things are being built, and it's done in investment cycles, and many times these investments are also delayed, or the technical building aspects of these are delayed. And so if the issue of price area deviations when you have transmission constraints is can you solve this with some of the larger demand projects from the steel industry that we're talking about, for example. And now, if it's operating close to what we would say base load, you can effectively see that it can counteract the price area deviation by soaking up large parts of this energy surplus. And as you see on the right-hand side, we still have, given that we have quite a lot of wind projects that are available to be built, the energy surplus can stay intact also in the long term, even though you deploy a lot of these larger demand projects, which requires a lot of electricity for their hydrogen production. Now, what this does is it turns to this virtuous cycle of build again. So even though we have these large price area differences, you have this virtuous cycle of build that start. So and this can keep the energy surplus relatively high, as effectively the Swedish northern regions aren't really resource constrained, and at very least not until 2030. And we also have a large amount of wind projects that are ready to be built if they can find finance. Now, if all the ambitions of these like hydrogen projects from the steel industry come to fruition, then we might see some resource constraints during the mid-2030s, and more wind projects will have to be developed locally if it has to be done up there. But obviously, you also have these offshore projects that could be developed in that case. But onshore wind is one of the cheaper ways to create renewable energy and to provide cheap electricity for hydrogen production, pretty much. So on the final slide, next slide, this shows a little bit the effect of this merchant build cost parity timeline effectively on the average Nordic system price and the variation it might have when we model effectively the Nordic power price by using a lot of different weather variations. So the Nordic power prices are very much dependent on hydrological situation and hydro inflows. So the only correct way to model it is to look at many different weather years and see the differences that it can create in the power prices. Now, if you start to look at deploying a lot of renewables, then this kind of variation in power price actually increase. But once you start to find this merchant deployment of electrolysis, which can soak up low price hours, this volatility effectively goes in the opposite direction. So you are able to limit the very, very low price hours in the very long term, even though you keep on increasing renewables in the Nordic market. All right, that is the final slide on the power market implication. And I think we get to key messages.
Thank you, Marcus. Yes, so we have reached the key messages, and we have 6 of them. So the first one is that the demand for green hydrogen will increase due to its role in decarbonization. And the second one is that Sweden has the right prerequisites for large green hydrogen infrastructure. And we have also the competence need in hydrogen technologies is a challenge, and that should not be underestimated. And then the fourth one, rather than local site hydrogen production, and based on the forecasted growth of the Swedish onshore RES, it is expected that planned large wind farm clusters will be better equipped to enable an optimized supply for hydrogen production, which is an attractive for regional demand. And on the fifth one, electrolysis pairs well in markets with high solar and wind penetration, making a potential case for future merchant builds if technology costs keep falling. And then the last one, as electrolysis deployment increases, it's likely to play an increasingly important role for the electricity price by supporting prices at times of high renewable output. And finally, we have come to the Q&A. And as I said before, the slide pack and recording will be emailed to all attendees as soon as they are available. And now the time is, we have still a few minutes left for questions. And the first question that has come in is, I would like to know how to transport hydrogen safely, and I would like to give that question to Pedro.
Yeah, well, there is different ways of transporting hydrogen in a safe way. There is different ways of transporting hydrogen generally, but the key issues or the key things that we should look at is that we should follow the regulations that are existing at the time being. And the regulations are, of course, regarding which kind of state we are, physical state we are producing hydrogen. If it's in gas form, then we would be able to look at, for example, Pressure Equipment Directive, which regulates how for example, the cylinders or the gas storage should be dimensioned and should be handled. Then there are also different regulations regarding hydrogen as a gas. For example, hydrogen has certain properties, which is it's a very light element and it should be approached in a different way. For example, gas fittings and gas connections should be done in a way that they are easily detected if any leakage occurs, for example. Sure, hope that if there would be more explanations, I'm glad to answer these by email if it's necessary.
Yes, and I think that's the case for the rest of the question as well, because time flies and time is up. And I would like to thank you all who have attended this webinar and for your attention and the time. And I wish and I hope that we see each other soon again. Thank you.